Hello, everyone. Thank you for joining us again at our latest installments of the Australian Geometric PDE seminar series. As you may recall, this year the focus of our seminars is we have our ECR members telling us about their research that they've been doing. Today, we're pleased to have joining us Qiyu Zhou, who's currently a PhD student at the ANU. He's going to be talking to us about high codimension mean curvature flow. Thank you, Hugh.
Yeah, thanks, Tim. Yeah, I'll be talking about high codimension mean curvature flow with one space-like codimension. So the background space is a pseudo-Euclidean space with one space-like codimension. I'll explain what this means in a bit. This is a joint work with my supervisor, Ben Andrews. Okay, let's get started. Uh, yeah. So first of all, I'll talk about some existing results in high codimension mean curvature flow. Then I'll talk about our results on curvature pinching and non-collapsing. Then finally, stability, which leads to a Huisken type theorem in this particular setting. Okay, so first of all, in codimension 1, mean curvature flow of hypersurfaces. So we say that a family of time-dependent immersions, F, where I here is a connected interval, satisfies the mean curvature flow if the immersion flows in the mean curvature direction. So here nu is the unit outward normal. A standard example is the shrinking sphere. So if you consider a family of embeddings of spheres parameterized in this way, then if the radius satisfies this equation, then it's a solution of the mean curvature flow. Then you can see that the radius is decreasing through the flow. So no matter what radius you started with, it shrinks to a point in finite time. And it's asymptotic to a round sphere. So we also have some classical results for hypersurfaces. So this is the Huisken theorem in 84, that if you start with a convex embedding, then this embedding stays convex and it stays as an embedding for all time. And your hypersurface converges uniformly to a point. And if you rescale it correctly, you can see that the limit is asymptotic to a round sphere. For dimension 1, we have something better. So Gage and Hamilton in 86 proved that if you start with a convex curve, then the statement is pretty much similar to Huisken's theorem, that it converges to a round point. And Grayson in 87 proved that you can remove the assumption of being a convex curve, then the result is the same. Okay, then what about in high codimension? Well, uh, the setup is pretty much similar. So here, if we think about the Euclidean background with codimension k here, then it satisfies the mean curvature flow if the immersion is flowing in the mean curvature direction. But here, there's no canonical choice of normal here. And here's a result by Ben Andrews and Charlie Baker. So if you start with a closed and smoothly immersed surface of dimension n, and you have non-zero mean curvature in this sense, and it satisfies a pinching condition where the little h here is the second fundamental form, and c here is a dimensional constant. So once you have that initially, then the mean curvature flow has a unique smooth solution on a finite maximal time interval, and it converges uniformly to a round point. In the sense that it's asymptotic to a sphere in some n+1 dimensional subspace of Rm plus k. And here I have some references for other directions in high codimension mean curvature flow. People have considered the flow in spheres, Asian solutions, singularity formation, all with Euclidean background. And here, a flow in complex projective space. And one that's very similar to our flow, that in pseudo-Euclidean space of arbitrary time-like codimension. Okay. Now I want to talk about what pseudo-Euclidean space is. So if you're familiar with special relativity, then the setting is k equal to 1 here, but we do this in general. So this is just a real vector space of dimension n+1 plus k, equipped with a non-degenerate bilinear form. And this condition here is saying that you can find an also normal basis such that E1 through En+1 is space-like in the sense that its norm is greater than 0. And these new 1 through new k's are time-like. And here we adapt some terminology from relativity. So we call a vector in the ambient space time-like if its norm is less than 0, null if it's equal to 0, and space-like if it's greater than 0. In the first two cases, we call this vector causal. So here's an example of what the space looks like for k equal to 1 and n equal to 1. So normally you pick a time orientation, so it makes sense to talk about future and past for time-like vectors. So the set of time-like vectors has two disconnected components. And if you're inside the cone, then the vector is time-like. If you're outside, then it's space-like. And if you're on the cone, then the vector is null. And in our setting, the normal space is R1K. So it's similar to this diagram here, but we reverse the rho of space and time here. And note that this description for the ambient space is not exactly correct when k is greater than 1. In that case, you no longer have two disconnected components here. Okay. Okay. In our setting, it's still the similar setup. We still flow in the mean curvature direction, and the ambient space is now Rn+1, comma k. So we have an n-dimensional space-like submanifold, and you have one space-like codimension here and k time-like codimension here, and k can be any integer. Our initial submanifold is space-like mean convex. What this means is that it must be space-like first. So being a space-like submanifold means that the induced metric on the submanifold is Riemannian. If in addition, its second fundamental form is space-like, in the sense that the second fundamental form applied to the same vector is space-like for all unit tangent vectors, then it's called spacelike-convex. And it's space-like mean convex if its mean curvature is space-like and non-zero. Those are very natural analogs of what convexity means in this ambient space. I'll explain why in a sec. And it's important to note here that the normal space has the structure of a Minkowski space-time with space and time swapped. And here's an example of what a space-like convex curve is. So this is in R21, and the first two coordinates are space coordinates, and the last one is for time. And here's a simulation of what happens under mean curvature flow. So the blue curve on the outside here is our initial curve. And on the mean curvature flow, well, first it shrinks, then it seems like it settles on a particular space-like plane. Then once that's done, it follows the usual mean curvature flow and shrinks to a point. Okay. The first result is curvature pinching. Uh, no, sorry, I didn't include what the definition of pinching here. But first of all, we need to talk about the preservation of mean convexity here. So of course, the flow preserves space-like convexity and mean convexity. And here's a additional constraint that your submanifold has to stay space-like throughout the flow. This is for maximum principal purpose. And here I've included a short proof for the preservation of mean convexity because it's very short. So this is the evolution equation of the mean curvature. And if you compute the norm squared of mean curvature at a minimum point, you have that the gradient of h is orthogonal to h. And by assumption, our mean curvature is space-like, and the gradient lies in the normal space. So there's only one space-like dimension in that space. So this tells us that the gradient is either time-like or zero. So if we look at the evolution equation of norm squared of the mean curvature, you get this expression here, where the gradient here is this nabla h term is less than or equal to zero. And the first term gives you the term on the second line. So this is always greater than zero at a minimum point. And that proves the result. And we have some characterization for compact space-like convex submanifolds. So for curves, we need to assume it's simple and closed. So the turning number of the curve is 1. Then we have the following result that that it must be acausal and diffeomorphic to n spheres. Here, acausal means that every pair of points on the submanifold has space-like separation. So that means that you can only connect the 2 points on your submanifold by a space-like curve. So the tangent vector at each point of your curve can't be causal. And in the proof of this result, we find that you can, for each decomposition of your ambient space, you can find Gauss map here because of this, because the intersection of the normal space and this particular space-like part must have dimension 1. Otherwise, that would indicate that the normal space has more than one space-like dimensions. Then here's a little result giving an orientation to the space-like vectors. So if you recall that in R1K, there's two disconnected components for the space-like vectors in R setting, and the main curvature is space-like. So we give an orientation by saying that for any non-time-like vector in the normal space, it's inward pointing if it lies in the same cone as the main curvature. Otherwise, it's outward pointing. And in our setting, we have two pinchings. So it's either inward or outward pinched. So it's inward pinched if HVV minus alpha H for some positive alpha is inward space-like for all unit vectors. And it's outward pinched if it's an outward space-like for all unit vectors. And we have shown that the flow preserves pinching. So I want to explain to you what pinching means in this context. So here's an illustration. If the normal space is just R11, it's easy to see. So H hat here is the unit direction in the main curvature direction. And alpha, beta here are the pinching constants. And nu here is some unit time-like direction orthogonal to the main curvature. So what pinching means is that the second fundamental form has to lie in this diamond-shaped compact region. This in the relativity terminology is called a causal diamond. And we need to talk about non-collapsing because once you have pinching, the standard way to get to Huisken's theorem was doing Stan-Pacquiao iteration to improve the pinching. But here, we only know that the second fundamental form is space-like. We do not know the causal character of any higher derivatives. So at different points, the gradient of the second fundamental form could be space-like, null, or time-like. That is not fixed. So first of all, I want to remind you about the hypersurface case of non-collapsing. So here, N, we denote the unit outward normal. Then we define this extrinsic ball curvature given by this. And two copies of the separation in the normal direction divided by the norm squared of the separation. And, oh, sorry. And you take the supremum and infimum of this expression. What this expression represents is the curvature of the ball touching at x. So it's clear in this diagram. So I say the point x2 here. So k underscore gives you the smallest ball touching at this point, the curvature of the smallest ball touching at this point. And and we have it's a bit different in our case, but in the hypersurface case, you see that the interior touching sphere is always contained in the submanifold. And in the main convex case, you would have the case that the exterior touching sphere does not contain the submanifold. So at point x1 here, you have a ball touching from the outside, but here at this point you have a ball touching from the outside that contains the whole submanifold. And the idea of non-collapsing is you can compare the curvature of those touching balls with the mean curvature of this of the surface. So, so you say that the mean curvature flow is interior delta non-collapsed. If there's some delta such that the extrinsic ascribed ball curvature is comparable to the mean curvature, and we call it non-collapsed if it's both interior and exterior non-collapsed. And it has been shown that for mean convex hypersurfaces, if you start with a compact mean convex initial data, then it preserves non-collapsing. So in particular, this gives you a comparison between the maximum and minimum mean curvature at each point. And in our setting, we want to do something similar. So we define the same quantity here that corresponds to the curvature of the touching balls. And here, because we don't have a canonical choice of normal, so here we pick n to be any inward non-time-like normal vector. And if it's unit space-like, then we have a similar interpretation as in the hypersurface case. But instead of having balls touching the surface, we have pseudospheres, which is spheres in Rn+1k, which look like hyperboloids. So here's an illustration. So at the point x here, if you consider non-collapsing in the mean curvature direction, then you have a pseudosphere touching from the inside in this sense. And you have this orange pseudosphere touching from the outside. And note that in this case, this exterior touching pseudosphere contains your whole submanifold. But it doesn't make any sense to talk about the submanifold containing the interior touching sphere. And similar to the hypersurface case as well, we want that the curvature of those pseudospheres comparable to our mean curvature. But there's some difficulties. So there's no, and the set of unit inward space-like vectors is non-compact. So in the hypersurface case, you take the supremum over the points, y not equal to x, to talk about the largest or largest touching pseudospheres curvature. But here you have an extra variable that lies in a non-compact set. So if you just take the supremum or infimum over that non-compact set, it might not be achieved. So what we need to do here is define this quantity here, Q. That is you compare the touching spheres curvature with some copies of the mean curvature in the same direction. And here you take the infimum and supremum similarly, but the extreme values taken over the normal directions have to be a bit careful. So what we need to do here is take all the null vectors that lie in the same space-like cone with the mean curvature with an additional normalization condition. So once you do that, this set is compact and topologically it's diffeomorphic to SK minus 1. Why do we do that? Because something special happens in Minkowski space. So, so in the normal space, a vector is inward space-like if and only if its product with any inward null vectors is greater than 0. So we only need to consider null vectors in this case, and the result would carry out to all the space-like vectors. And similarly, we say that a mean-convex submanifold is delta exterior non-collapsed if Q underscore is greater than or equal to 0, and interior non-collapsed if Q bar is less than or equal to 0. And we've shown that non-collapsing is preserved under the flow. So here's some implications from non-collapsing. If you have an embedding and your submanifold is compact, space-like-convex, and non-collapsed, then you have the following bound on Lorentzian distance. And this implies the comparison between maximum and minimum mean curvature. So as you can see that when delta plus approaches delta minus, this tends to 1, but it doesn't give as strong as the results as strong as in codimension 1 case. The most important implication is that the hyperbolic angle between the mean curvature at different points is bounded. By that, I mean that if you fixed a decomposition of your ambient space, so for simplicity, you can take the tangent space at one point for a fixed x, then you add the mean curvature direction at that point. So that gives you a copy of Rm plus 1. What you can say is that the angle between the mean curvature at a different point y with any time-like direction that is orthogonal to this plane is bounded. Why do we want that? Well, because this estimate here is independent of the point y here. So once you fix an x, this constant is fixed. And this allows us to find an inner product on the space such that the second fundamental form is bounded in this sense. So you can find an orthonormal basis for some purely time-like subspace such that the inner product defined this way has the second fundamental form bounded. So this extra expression here just reverses the time-like direction. And the bound on the second fundamental form only depends on your initial constants for interior and exterior pinching. And since, not pinching, sorry, non-collapsing, then since it's preserved under the flow, then as long as the flow exists, then you have this fixed inner product such that your second fundamental form is bounded. And the choice of that was just fixing this particular maximal space-like subspace, then reverse the time-like directions. And this gives us a way to do smoothing and long-time existence. So we define long-time existence in terms of this new Euclidean inner product. We call it a solution to mean curvature flow singular if its maximal exist time is less than infinity and the second fundamental form blows up. With the new product, we found the following gradient estimate. So you can find some tau that is less than the maximal time, such that the gradient, the higher derivatives of the second fundamental form, is bounded by this quantity here, where this constant here is only dependent on n, the order of the derivative, and nk, the space-like and time-like dimensions on the ambient space. And this gives us the long time existence result. And once you have that, you can do a sort of parabolic rescaling to your flow and find a subsequential convergence. So this leads to the idea of stability. So first of all, you need to find some subsequence such that your flow converges to a sphere. So we proved this year that you can find such a subsequence, and the subsequence is given by this. So you rescale the flow parabolically. So this is the standard parabolic rescaling. Then since our Euclidean product is dependent on the choice of which decomposition you pick. So for the time equal to 0, you pick this P to be the direct sum of the tangent space at one point with its mean curvature direction. So at each point, you need to rotate the space such that at least one point on your manifold such that the tangent space with its mean curvature direction matches this particular maximal space-like subspace. That's why you need to do this rotation here. Then once you have that, you can prove subsequential convergence result. Then we did a stability argument to show that if you consider a normalized flow in some sense, then the flow is stable around this final n sphere in some n+1 dimensional space-like subspace. So I'll give you an outline of how we did it. So for this fixed and Rn+1, we consider this normalized flow. So we fix the volume by this additional term here. And we also fix the center of mass for the submanifold, that for a sphere is just 0 in some n+1 dimensional space. And a rotation L here, such that the minimum projected volume is attained on this particular space. So here's some expressions for what those are. A for scaling, the scaling for volume should be of this expression, and fixing the center of mass, the B term should have this expression. And there's no closed form for the rotation here, but it doesn't affect the argument later. So remember that we have this subsequence that converges to a sphere. So we're only considering space-like convex submanifold. So recall that there's a result before that it is diffeomorphic to a sphere and acausal. The proof there gives us a Gauss map parameterization. So if you fix a decomposition of your ambient space, then for this particular P here, you can find a Gauss map. And once you have that, you can also find the support functions defined this way. So the sphere here lies in this particular copy of Rn plus 1, which is P here. So you can find that expression for the support function is just your product with the coordinates on Z and the inverse of your Gauss map. And we have the following parameterization of the spacelike-convex submanifolds. So the first two terms here is exactly the same as how you parameterize a convex hypersurface. And the last term here just adds the timeline components back up. Then on a sphere, sigma is 1, and those timeline components are just 0. So the stability we had is this. So the L2 norm of sigma and all those timeline components decreases exponentially. Well, if they're initially small, but this is guaranteed by the subsequent convergence. Then you can do an interpolation to get the exponential convergence of the CK norms. So this is a special version of the Gagliardo-Nirenberg interpolation. Then once you have that, then this gives you an exponential convergence for the rotation in so this particular term in the normalized flow. So once you have that, you need to relate the normalized flow back to your mean curvature flow. And you can do it this way. So this F here stands for the normalized flow. So you want to consider a scaling psi here and a rotation r here and t a translation here that gives you back the mean curvature flow. And it turns out that if you choose all of these, then it gives you back the mean curvature flow. And the second one is of great importance here because if you solve this ODE here, because L converges exponentially here, then we must have R converges exponentially here. So if you look back at the rescaled flow, then this just indicates that it converges to some sphere rotated by whatever this R converges to. And this proves our main result. So if you start with a space-like convex embedding, then throughout the flow it stays space-like convex and embeddedness is preserved. Then the flow converges uniformly to a point, and with that parabolic rescaling and rotation, it converges in smooth topology to a smooth embedding, whose image is just the standard round sphere in some Rn plus 1. So for n equal to 1 here, this is an analog of Gauge-Hamilton theorem. And I'll stop here. Thanks.
Thanks very much for taking us through all this work, Qiyu. Let's thank the speaker. Does anyone have any comments or questions for our speaker? Obvious question, higher space-like terms. Do we know what happens there?
No, and it's not as nice as this
I
setting.
can certainly believe that.
Yeah, I think that gets back to the high codimension Euclidean case as well.
Okay, so this is, I see.
Yeah.
Cool. Thanks.
Mm.
You had something you wanted to add, Ben?
Not really, no. Just in this setting with only one only one space-like codimension, the really nice thing is you do have this analog of convexity. As soon as you add more space-like convections, that falls apart, and you don't have a preferred.
So you're stuck. You don't even know what the right condition is.
You're right. There's, the condition in this old paper of mine with Charlie, we had kind of a very simple, the most naive possible pinching condition you could put on, which is some sort of quadratic pinching on the second fundamental form. And that's clearly not the right condition. It's just the only one we can do. But in this setting, we have something much more natural. Yeah.
Okay. So in some sense, this is better than what happens if you're in the purely Riemannian setting.
That's right. Yeah.
Yeah.
That's quite. I despair a little bit at hearing that because I always get nervous when I feel like I need to go from Riemannian to Minkowski all Lorentzian signatures. Well, no, that's exciting. Does anyone else have anything else they'd like to add or comment on or question at this point? All right, then in that case, let's thank Qiyu again for taking us through this work.
Thanks.
Awesome. Thank you, everyone.